So good afternoon. My name is Luís Kadowaki. I'm a postdoc in the Department of Astronomy of University of São Paulo, and I would like to thank the organizers to give me the opportunity to present my work that has been done in collaboration with Professor de Gouveia Dalpino, Tânia Medina Torrejon of University of São Paulo, and Professor James Stone in Princeton University. So, in this talk, I will speak about turbulent fast magnetic reconnection in accretion disks and the numerical simulations that we have performed to reproduce AGN instabilities in such systems. Finally, I will describe the algorithm to identify fast magnetic reconnection in the surrounds of the accretion disks and our recent results of the identification of fast reconnection in general-relativistic AGN simulations of thick disks and special relativistic simulations of point flux rotating jets. And finally, I will present our conclusions. So, as you know, accretion disk systems are believed to be very common structures in the universe. These systems are associated to black hole binaries, AGNs, and younger stellar objects. The formation of a turbulent corona above and below accretion disks plays an important role in the magnetic reconnection events. So these events could explain, for instance, the flare X-ray emission from younger stellar objects and the radio and gamma ray emission from black hole binaries and AGNs as well. So, for instance, recently, gamma ray detectors have observed very high energy emission from black hole binaries and low luminosity AGNs. These emissions are characterized by fast variability, which corresponds to very compact emission regions around 100 or 100 of Schwarzschild radii. So, if the gamma ray emission comes from the inner region of black hole binaries and low luminosity AGNs, where the particle shock acceleration is less efficient, we can make at least two questions. For instance, where are the particles accelerated and what are the real acceleration mechanisms of the particles? So, the answer of these questions can be the magnetic reconnection process. Turbulent fast magnetic reconnection can be a powerful mechanism operating in the core region of black hole binaries and the low luminosity AGNs. And this is were demonstrated by Kadowaki et al. And Sign et al. In 2015. For instance, this diagram obtained from Kadowaki et al. Shows in grayscale colors the magnetic power released by turbulent fast magnetic reconnection as a function of the black hole masses. The symbols correspond to the gamma ray emission, the radio and gamma ray emission observed from black hole binaries, low luminosity AGNs, blazars, and GRBs. The diagram indicates that magnetic reconnection is enough to explain the gamma ray emission observed from black hole binaries and low luminosity AGNs, while the very high energy emission observed from blazars and GRBs don't have any correlation with the magnetic reconnection power, as we expect, since these emissions probably comes from the jet propagating far away from the inner region of the sources. For more details about the particle acceleration mechanism by magnetic reconnection and how to get the SEDs of the sources, you can see the talks of Professor Elizabeth de Gouveia Dalpino and Juan Rodrigues Ramirez tomorrow. So, several models have been developed to explain the magnetic reconnection mechanism. In this work, we are interested in the model developed by Lazarian and Vishniak. In this model, the magnetic reconnection will be triggered by turbulence, in the sense that we have several magnetic reconnection points at always all scales occurring at the same time due to the wandering of the magnetic field lines. Because that, the magnetic reconnection will be fast in the sense that the reconnection velocity will be the order of the Alfvn speed. This model was successfully tested numerically by Koval and collaborators in 2009 and 2012. So, to check the viability of the magnetic reconnection events in the inner region of black hole binaries and low luminosity AGNs, we have performed MED numerical simulations of accretion disks and corona. So the aims of the first part of this work were the formation of a large-scale poloidal magnetic field by the arising of loops due to the PRTI, the Parker-Rayleigh-Taylor instability, and the role of PRTI and MRI, the magnetorotational instability, in the formation of a turbulent magnetized corona around the accretion disks, where we believe that magnetic reconnection will occur. Finally, the last aim was the identification of fast magnetic reconnection events by the statistical analysis of the reconnection rate in the corona and in the disk separately. So for this, we have performed local 3D MED numerical simulations employing a shearing-box approximation. In this approximation, a steady flow with a linear shearing velocity is applied, considering a Keplerian disk profile. This method is used to study small parcels of the accretion disk in a high-resolution computation domain. This is an example of one of our simulations where it's possible to see the formation of these two important MED instabilities. One of them is the MRI. So in this instability, a weak magnetic field exerts an elastic force between two elements of fluid, and because that, this force will transfer angular momentum from the inner region to the outer regions of the accretion disk, making possible the accreting in a Keplerian regimes. During the linear regime, the magnetic field will be amplified by the MRI due to dynamo effects that has strong implications in the formation of a large-scale poloidal magnetic field in the coronal region of such systems. And during the nonlinear regime, the magnetic field will saturate, and the MRI will trigger turbulence inside of the system. So, in the case where the accretion disk has strong azimuthal magnetic fields perpendicular to the gravity, the PRTI, the Parker-Rayleigh-Taylor, will set in, producing magnetic loops in the coronal region and helping the formation of magnetic reconnection sites, like those occurring, for instance, in the solar corona. So, as I have mentioned, we have reproduced such instabilities by 3D MED numerical simulations. These simulations were performed using the Athena code developed by Stone and collaborators. And as initial conditions, we have used a stratified isothermal system in magnetostatic equilibrium, and with a strong azimuthal magnetic field with the beta parameter, the ratio between the magnetic pressure and the thermal pressure of the order of the unit. This diagram shows the time evolution of the system, where it's possible to see the Parker-Rayleigh-Taylor instability and the MRI acting inside of the system and the formation of the turbulence. The background colors in this case correspond to the density profile, and the streamlines correspond to the magnetic field lines. The same behavior is seen in these two diagrams that show the time evolution of the beta parameter here and here, and the QRF, or the current density of the system, here and here. And again, the streamlines correspond to the magnetic field lines. Here, it's possible to see, even with an initial high magnetized regime, the disk will evolve to a gas pressure dominant regime, as we expect, since the magnetic field will be transported from the accretion disk to the coronal region due to buoyancy effects. This will strengthen the role of the magnetic reconnection in the coronal region of such systems. So with these simulations, we have evaluated the magnetic reconnection rate by an algorithm to identify current sheets. So we have adapted the algorithm of Zarangin et al. And extended to a 3D analysis. Basically, this algorithm will select a sample of cells with a current density higher than a threshold. And the algorithm will check if these cells are between opposite magnetic field polarity. Finally, from this sample, we have evaluated the magnetic reconnection rate in a similar way to the method used by Koval and collaborators, where we have averaged the inflow velocity by the Alfvn speed over the inflow boundaries. This is a sketch of the magnetic reconnection region, where you have the magnetic fields with opposite polarities, and then you have the inflow velocity compressing the magnetic field lines in this region to make possible the reconnection. So we evaluate the magnetic reconnection rate by this way. So here we see the spatial distribution of the select points by the algorithm, where the background colors correspond to the current density of the system. The plots in the left and right correspond to the profiles of the velocity field and the magnetic field along the magnetic reconnection site. To evaluate the magnetic reconnection rate, we have selected a subsample of points where we just reject those ones with non-symmetric profiles, just to take the statistics of the system just in symmetric profiles, as you see here in these two diagrams. So, despite the challenge to represent magnetic reconnection events in 3D MAD numerical simulations, we have shown here an example of accept cell using the linear integral convolution method combined with the maps of the magnetic field and the current density. Here we clearly see the anti-correlation between the current density and the magnetic field in the middle of these two diagrams. Here, it's possible to identify at least 3 points. Unfortunately, the image is not too good, but the square symbol corresponds to an event identified by the algorithm, in the sense that the magnetic reconnection is occurring. And here and here, we have 2 magnetic reconnection sites where possibly the magnetic energy has already dissipated. The algorithm identified just this region where you have a maximum value of the current density. So we have evaluated the time evolution of the mean and the standard deviation of the magnetic reconnection rate, as you see here in these two diagrams that correspond to the magnetic reconnection rate in the corona region of the system and in the disk. So as you see, the mean values will vary between 0.1 and 0.2, indicating a fast magnetic reconnection, as we expect in a medium in presence of turbulence. And we have also evaluated the power spectrum of the velocity field in different heights of the system, from the middle plane of the accretion disk to the coronal region. Here we trace the traced line correspond to the Kolmogorov spectrum. As you see, the turbulence is not fully developed initially. It's not fully developed initially, where the magnetic reconnection rate will show values below 0.1. At 50 orbital periods here, where the magnetic reconnection rate shows values between 0.1 and 0.2, it's possible here it's possible to see the typical cascading of the power spectrum with a slope near to the Kolmogorov spectrum, indicating a possible correlation between the turbulence and the magnetic reconnection that we have measured in this work. So we have adapted the algorithm to measure the magnetic reconnection rate in a general-relativistic accretion disk. So our recent tests use the GRMHD model of the Athena code developed by Professor James Stone and collaborators. And here we have simulated a torus around a rotating black hole in a two-dimensional domain. So this diagram shows the magnetic reconnection rate measured by an observer at rest with respect to the coordinate grid, in this case, Fairchild coordinate grid. This test corresponds to a torus with a weak magnetic field that will be represented by closed loops inside of the accretion disk. As time goes by, the MRI will sets in, allowing the accretion process and the formation of a turbulent environment. At this point, we have measured magnetic reconnection, mean magnetic reconnection rates between 0.01 and 0.7. So we have also adapted the algorithm to measure the magnetic reconnection rate, but now in special relativistic numerical simulations of point flux rotating jets. So in this part of the work, recently Singh and collaborators have performed 3D MAD special relativistic numerical simulations of point flux dominated jets using the Haishin code developed by Mizuno and the collaborators. As an initial condition, they used a magnetic field with a helicoidal force-free configuration and a heavy jet, in the sense that the density of the jet is higher than the density of the environment. By an induced precession perturbation, a current-driven kink stability is developed inside of the system, and this will in turn induces turbulent and fast magnetic reconnection inside of this system, where we verify the efficiency of the magnetic reconnection here. This process can play an important role in the particle acceleration along the jet that will propagate far away from the central source of these black hole binaries, low luminosity AGNs, for instance. In that case, we have measured magnetic reconnection rates around 0.05, mean magnetic reconnection rates around 0.05. The red points here correspond to identified magnetic reconnection sites identified by the algorithm. At this point, I would like to mention the nice talk of Will Potter that he gave in this morning, and I would like to highlight the importance of turbulent fast magnetic reconnection along the jet to extract efficiently the energy from this kind of object. Finally, I would like to summarize our conclusions. Our simulations have revealed the rise of magnetic loops due to the PRTI, followed by the development of turbulence due to PRTI and MRI. Even with an initial high magnetized regime, the disk evolves to a gas pressure dominant regime with a magnetized corona that relates the transport of a magnetic field from the disk to the outer regions to the coronal region by buoyancy process. And we have evaluated the magnetic reconnection rates and detected the presence of fast magnetic reconnection as predicted by the theory of turbulence-induced fast reconnection of Lazarian and Vishniak. The algorithm applied to this work has demonstrated to be a very nice tool for the identification of magnetic reconnection sites in the numerical simulations. And our preliminary results in GRMHD numerical simulations of thick disks show magnetic reconnection rates around 0.06, it's fast. And likewise, our special relativistic MAD numerical simulations subject of the current dense kink instability indicate fast magnetic reconnection velocities around 0.05. So that's it. Thank you.